on Blackboard. Okay, so 2 shows up in X and Y, so that means we have to take it out. 3 also shows up over here in Y, so it'll be taken away. And the 6 we can leave alone since it doesn't belong to Y. So this is all that's left over after you subtract this set. And it's a good idea to flip the order around. Let's take a look at what happens if we start with X, we start with the second set Y, and then take away the elements of X. So 1 is in Y, and we are not taking it away, so it'll still be there. 2 is in Y, but it gets subtracted off. Same for 3. And then 4 is not an element of X, so that means it'll survive. So it's still there. Okay, any questions about these 3 operations? Okay, so most of you have probably seen them before in an earlier math class. The sets in this example were really small. Let's take a look at some bigger sets. How about the set of integers? And maybe the real numbers. Maybe we'll talk about the rationals as well. Okay, so the first question, what would happen if I took the integers and combined it through a union with the real numbers? So the integers are the whole numbers, so 1, 2, 3, 4, so on and so forth, 0, and then all the negative whole numbers as well. And I want to take them and union them up with all the real numbers. What would we get? Anyone want to try answer?
All the real numbers.
All the real numbers, good. So you might be wondering why nothing extra is here. What happened to Z, the integers? And the reason that we don't have anything extra is because the integers are already real numbers. So like the number 1 is a real number, number 2 is a real number. So when we take the union of the integers with the real numbers, we're not adding anything new. We're just left with what we already had, the real numbers.
So is integers a subset of real numbers then?
Yes. So we can put a little note maybe on the side that the integers are a subset of the real numbers. And in case you forgot over the weekend, this symbol, it looks like a sideways U with a line underneath, means subset. Let's try another one with these 3 threats. What if I take the real numbers and then subtract off the rational numbers? So what would be left over if I take my real numbers and subtract off all the fractions, quotients?
Would it be integer?
So the integers are actually in the rational numbers. We can add that over here. So z, the integers, is a subset of q, the rationals. The reason is a number like, let's say 3, is actually a quotient in disguise because 3 is equal to 3 over 1, for example. Or 3 is also equal to 6 divided by 2. So they are definitely, the integers are definitely in the rationals. So if I take away the rationals from the real numbers, that means there aren't going to be any integers left. What would be left? Can you think of a number? Irrationals, yes. So it's a little silly. We take the real numbers, we get rid of all the rational numbers, and what's left is the set of irrational. Irrational numbers. Okay. And I think I mentioned a few of these the other day. These are things like pi, the square root of 2, pi plus the cube root of 42. So these are all the slightly strange numbers that aren't fractions. Okay, good. Any questions about unions, intersections, set differences before we move along?
I'm still getting the irrational number.
So you're wondering what the irrational numbers are?
No, I'm still writing them down is what I mean.
Oh, you're writing. Okay, yeah, I can just take a second. Pause a second.
Okay, I'm good.
Okay. So the next idea is something that we mentioned before. So what I mentioned before is that a set can actually have sets inside of it. And this idea, a family of sets, is a set where all of the elements are actually sets. So it's not as weird or crazy as it might sound. So we just have a set, and then all of the elements are sets. So if I'm just sticking to letters, I could have something like this. Okay, so it's a set, and then everything inside of it is also a set. And this is what we call a family of sets. Or sometimes you might call it just a set of sets. Okay. So now we need this definition of disjoint because we're going to talk about the relationship of things inside of a family. And disjoint, kind of, it is what it sounds like. Two sets X and Y are disjoint if they don't have any elements in common. So what that means is if you take the intersection of the two sets, you should get the empty set. Okay. So we can do a quick example, maybe with letters again. So maybe the first 3 letters of the alphabet, and then we can look at the last 3 letters of the alphabet X, Y, and Z. If we tried to figure out what was in common between these two sets, well, there isn't anything in common. It means the intersection is the empty set. So that means these two are disjoint. So where you'll see this idea more often is in the context of families of sets. And a family of sets is, well, let's give it a name S. A family of sets S is pairwise disjoint if whenever X and Y are distinct sets of S, so they're elements in the family, their intersection should be empty. So I need a family of sets if I'm looking for an example, and they can't share any elements in common if they're going to be pairwise disjoint. Okay, so you could have something like this. If you look at the first set has A and B inside of it, and you compare it to any of the other sets, you can see that they don't share anything in common. And this should be an E to make that a little bit more easy to read. If I look at this second set and I compared it to everything else, they don't share anything in common. And the same thing if you look at the third set or the fourth set with X, Y, Z, or this last set with P and J. So none of these share elements in common. And that's what we call pairwise disjoint. And a lot of time in math, we're dealing with mostly subsets of a single set, which I'm going to call U. So maybe think back to if you've taken a calculus class or algebra, something like that. Most of the time, you're going to be dealing with real numbers, right? So that's an example of where everything that you're dealing with is the subset of the same set. So if you're looking at solutions to quadratic equations or things like that, you're looking at maybe the subset of the real numbers. Okay, so in this situation where everything is inside of this bigger set U, we give U the name universal set. So we think of U as our universe where everything happens. And we also get this new idea of a complement. Well, it's actually an old idea that we saw on the previous page, but it has a new name. If X is a subset of our universal set, then this U minus X gets a special name called the complement. So the idea here is that U minus X is everything in the universe except the elements of X. So let's say our universe is, to pick a slightly smaller example, the integers. And we might be interested, like we were in that homework problem, about the positive integers. So 1, 2, 3, 4, so on. I might care about what's not in my set as well. So I might want to figure out what X complement is. And there's this notation, which I didn't mention yet, of the complement of X is written this way. You take your set and you just put a bar on top of it. And this stands for the universal set minus the set x. So in this case, the integers minus the positive integers. Okay. So can anyone tell me what this would be? What the complement of x is?
Negative integers.
You're very close. Very close. So we do have all of the negative integers, but we also have another number.
0.
0.
Good. So you have to be a little bit careful when you say something like the negative integers or the positive integers, because the number 0 is neither positive nor negative. So just be careful with that. But yes, very close. Any questions? We're going to look at a picture next that I hope helps clear this up. Okay, so the next thing we're going to do is talk about Venn diagrams. So you probably saw these, you've probably seen them for a very long time. Going back to elementary school, I'm sure you could tell me what they look like. Okay, so here is a Venn diagram, like you might have seen. So we have two overlapping circles. You can have different numbers of circles in a Venn diagram, but this one's going to have two. And let me label some of these things in terms of the sets that we've been talking about. The first thing to do is to consider the box as a whole. And this box is standing in for our universal set. So everything lives inside of our universe, U. And then since I've drawn two circles, that means I have two sets that I'm considering. And let's label them X and Y. Okay, so far, I think everything here on the Venn diagram should be very familiar. But what I want to do is compare the picture of a Venn diagram to the kind of set notation that we've been talking about. So what I want to do is take each of these four regions, 1, 2, 3 here in the middle, and then 4, and try to write down what each of them are using the notation for sets. Okay, so 1, let's start there. That's the box. Everything in the box except my two circles. So what I need to do is take my universal set and subtract off these other two sets. And here's how we might write that. So I have my universal set U, and then I want to subtract off both X and Y. So I can take their union and subtract both of them. But there's actually an easier way to write this, slightly easier, let's say, because the universal set minus another set, that's just a complement. That's what we call a complement. So this is really just X union Y with a bar on top. Okay, so let's move on to the second region. So this is the area of X that doesn't overlap with Y. So if I can take my set X and subtract off all of this, I'll get what I need. So that's X minus Y. And then 3 is where the two circles overlap. So this area is in both x and y. And we called that the intersection. And then lastly, 4 is very similar to the second region. These are the parts of y that don't overlap with x. So that it's y minus x. Okay, so whenever you're looking at some set notation that might be a little bit hard to understand, one technique to kind of wrap your head around it and understand it would be to make a Venn diagram that represents what you're looking at in set notation. And that way you can have a better picture, let's say, of what's going on. So this down here is very abstract, and this Venn diagram feels, in comparison at least, much more concrete. Any questions over Venn diagrams?
So what if there were 3 circles?
What if there were 3 circles? So that 3 circles we can represent fairly easily, like so. So maybe we can label that one Z. And that's the picture that you would get. And you can see that it actually adds 4 new regions to our Venn diagram. So there's 1, 2, 3, 4 extra regions that we would have to consider.
But like, how would we do the math for those if that was the,
Okay.
there's
So
a
maybe we can label them 5, 6, 7, and 8. And let's just maybe do a couple of them, maybe 5 and 6. So for 5, we just have to see where it falls in the picture. So we're looking here, and this little region overlaps my new set Z and also the set X. So everything in this little segment is in both of these 2 sets. And that's just an intersection. X intersect Z. And one thing I should mention, if we redrew our picture like this, you would also have to change up some of these things because now they're a little bit different. But is this quite right? X-intercept Z, does that capture the full picture? So if we look, go ahead. So what did you say there, Nick?
I don't think it does capture the full width of it.
So the problem is actually that the intersection of Z and X would be both of these regions, 5 and 6, because you can see all of these elements here are in both of these sets, right?
Mm-hmm.
The circle and the circle. So we have to get rid of this somehow. Do you see a way that you might do it? So we want all of the elements over here, but not these. How can we throw them out?
The difference?
So we need some sort of difference, that's right. But what should I take out? What should I subtract?
The union of X and Y?
So I don't want to subtract out all of this. So I can't just take the union with Y and X. I can get away with just subtracting off Y. So if I subtracted off X, I would get rid of both of these. That's the problem. But if I subtract off just Y, then I can get rid of 6 without getting rid of any of this stuff. So we end up with this. We have an intersection, but then we also have to subtract something. So adding more sets to our picture makes this sort of thing more complicated to write down. So as you might expect, if you add more stuff, it gets complicated.
Okay, so if we wanted to know just one element, it would be just the difference minus the intersection, right?
What you said, one element?
Like say we wanted to know just y, but not x and z.
If you just want the elements here, but not any of these, yeah, so the way it's drawn now, that would be region 4. So this stuff. Yeah. So you would have to subtract off both of these sets, the union. That's right. Okay, so the next thing on my notes, and I'll have to zoom out for this since it's kind of big. There we go. Okay, so the next thing that we need to discuss is this theorem. So this is how it's labeled in your textbook if you need to look it up. Theorem 1.1.22. It has parts A through K, which kind of aren't even in the picture. And this collects lots of properties that you need to know about sets. We're not going to go over all of this in detail today, but you might want to take a look at this and become a little bit more familiar with it. But we'll return to this theorem in chapter 2 when we actually, or when you guys actually prove these statements on your own. I can maybe point out a couple of them that are important, like A is called the associative property. So you've probably heard the word associative in a previous math class. And what it does is it tells you that you can move the location of the parentheses. So over here I have the union of A and B grouped together in parentheses, and then I union with C. But it actually doesn't matter how I group them. I could group B and C together and then take the union with A. And thinking back, I guess maybe to your algebra class way back in high school or middle school, just to pick an example, we can group how we add numbers any way we like. And this was also called the associative property. That's where the name comes from. And the same thing works for intersections. We can move parentheses. So intersections and unions. Part B, this lets me change the order of things in a union, or I can change the order of things in an intersection. And we call this the commutative property. So commute for move. And then part C, it might be a little bit hard to see it since there's all these sets running around in intersections and unions. This is actually just like the distributive property that you know from algebra. So the distributive property is when you have things like this, 2 times something in parentheses, you can distribute the multiplication to each thing inside the parentheses. So it's 2 times x plus 2 times 3. The same thing is going on here, except it's sets instead of numbers. Inside my parentheses, I have a union, and then I'm intersecting the set A with the union. And this intersection with A gets distributed to each of these sets in the parentheses. So A intersect B and A intersect C. And then since there was a union symbol in between inside the parentheses, I put a union symbol here in between the two intersections. And then I'll let you take a look at this one too. We've just interchanged. Here we have an intersection and a union. In there I have a union and an intersection, but it works the same way. And the rest of these properties don't, well, except maybe one or two, don't really have these big names. They're not really super closely related to things that you know before. But they're good to think about if you take a minute. For example, D, this first part, we have A union with the empty set. So I'm taking some set and I'm adding nothing to it, and nothing happens. So this is like adding 0, for example. And just keep on going down to the bottom of the page. This last one I should point out as being important. It's called De Morgan's law. And let me explain what's going on. So inside the parentheses here, I have two sets, A and B, and I'm taking their union. But then on the outside, I have a complement. And the way that this complement distributes into the parentheses is like this. So you take the complement of each of the sets inside of the parentheses, but this union gets flipped upside down. So I literally take the symbol and I flip it upside down, and it becomes an intersection. And the same thing happens to intersections. If I distribute my complement into the parentheses here, the intersection gets flipped upside down to become a union. Okay, so like I said, they are important, and we will definitely be coming back to these parts of the theorem. So make sure you read over them and maybe try to think about them a little bit, and we'll be coming back in the future.
What's that one I where it's got the A with what looks like an equal sign over it?
Okay. So it's actually an A with two complements on top of it. And there was a question about, have we discussed everything on the homework that's due? I do have one short page, or not even a whole page left of notes that we're going to go over here in a second, and then we'll be done. Then we'll have done everything for the homework. Okay. So maybe we can talk through what's happening here. So I have the set of A, and A with a complement is, in rough terms, the set of everything not in A. Okay, and then what I'm going to do is take another complement. Okay, and this basically puts an extra not in here. So this is the set of everything that's not in A.
So basically, it's everything that is in A.
Exactly. So in normal English, we're not allowed to use double negatives like this, but they do happen in mathematics sometimes. And they work exactly like minus signs. If you have two minus signs, they become a positive. And if you have two nots, they become, well, they cancel each other. They just go away. So everything not in A is actually just everything in A. Good. Okay. Any other questions before we move on? I know a lot of this is going to be, well, it'll take you a while to absorb it, but it'll happen. So moving on to the last few things, we're going to talk about families for a minute again. So we're going to start with a family of sets, S, and I want to talk about the union of the family S. And this is basically the same as the unions that we were talking about on the last couple pages, but now we're taking the union of all of the sets in S. So we're just taking all of the little sets that live inside of this family, and we're adding them all together to get the union. And here it is in set builder notation. It's the set of X such that X is in one of the sets, capital X, that lives in the family, S. And for this example, I want to start talking about bigger sets because we have to be able to think about them. So my family is going to have an infinite number of sets inside of it. And I'm just going to label them. Okay. So S is going to be a big set. It's going to have A1, A2, A3, A4, A5, and off to infinity inside of it. So next I have to tell you what each of these guys is. So what is A with a little subscript? Okay. So AI, it'll depend on the number, is going to be equal to the positive integers starting at I. So I plus 1, I plus 2, I plus 3, and so on. And that's still a little abstract. So let's just think, what's an A1? Well, that'll be 1, 2, 3, 4, and so on. And then A2, we'll start at 2, and then count up. So 2, 3, 4, 5, and so on. Let's find a little bit more room, maybe up here. What would A42 be? It's the same idea. I start with 42 and just count upwards. So 42, 43, 44, off to infinity. Okay, so this is my family. I have my family S with an infinite number of sets in it, and each of my sets is actually infinite, and you're just counting whole numbers off to infinity. So the question here for the example is, what is the union of the family S? What happens if I take up all of these sets and I put them all together?
Would it be A infinity?
A infinity. So what would that mean?
Like it would kind of take place of where the I and the ones and
So you're thinking like infinity. Let's see, where's some scratch space down here. So do you think it's infinity plus 1 or infinity and then infinity plus 1?
I would say just infinity and then infinity plus 1.
Okay. So the thing to remember, and it might be a while since you've had to think about this, is that infinity is not actually a number. It's more of an idea or a concept. So it's kind of the idea of never ending. Like you could count forever. That's what the idea of infinity is. So infinity plus one, you can't really add one to infinity because, well, it's not a number. Any other ideas?
A minus 1.
So that's where you would start at -1 and then do 0, 1, 2, 3.
No, I mean the set of A minus 1.
Just subtract everything, subtract 1 from everything.
Yeah.
So that we would start at 0.
Yeah.
Okay. But when I take the union of my family, I'm just adding up all of the elements. I can't add anything new to my family. 0 isn't over here, so I can't add it in. Okay, so let me tell you the answer. It's actually just a 1. And I'll explain a little bit. So the idea here is that we start with A1, and then we might want to take the union of A1 with A2. So we take all the numbers 1, 2, 3, 4, so on, and then we add in 2, 3, 4, 5, and so on. But all of these numbers in A2 are already in A1. So when I union these two sets together, I don't add anything. And if I add in A3, I'm going to add in 3, 4, 5, 6, and so on. Those are already there too. Even something like A42. I didn't write out 42 numbers, but 42 is in the list already. So is a billion and a trillion and all those other huge numbers. So we're not actually adding anything. We just have this first set. So if you have any questions about that, feel free to ask them. Otherwise, we'll talk about the intersection of the same family. So I still want the same sets of counting numbers, but now instead of looking at the union, adding them all together, I want to talk about the intersection. And the intersection of a family is just everything that's in each of the sets. So it's the set of X such that X is an element of a set X for all of the sets. So if something is going to be in the intersection, it has to be in each of these things. So it has to be in A1, A2, A3, A1000, etc. So any ideas or thoughts on what might be here? Yes, someone just said the empty set. That is correct. And let me explain. So just pick any number. Let's say 1. 1's a good number. Is 1 in the intersection? Is it in all of the sets? The answer is no. Go ahead, Nick.
I was just saying no in agreement.
Okay. So the reason is that 1 shows up in this first set, but it's not going to show up in A2 or A3 or A4. And if I pick any other number, let's say 1,000, 1,000, it'll be in these sets that I've written, and this one too, but it's not going to be in A1001 because we start at 1001 and then count up from there. And the same thing holds true for any number that you can think of. If you start at a high enough number set in your list, then the number that you're thinking of is going to be missing.
So for that answer, could we just do like the symbol for the empty set?
Yes. Yeah, just the circle with a slash through it. That's fine. Okay. So now let's step back a little bit from these huge sets in that family and talk about ordered pairs here. So this is the last thing that we're talking about from this section. Thankfully, this first section is kind of long and has lots of dry definitions in it. So ordered pairs come from Cartesian products. The Cartesian product of two sets x and y is just the set of ordered pairs from the set. So the first element in your ordered pair comes from the first set, and the second comes from the second set. And there's a little bit of notation here. If you want to talk about the set of ordered pairs, the Cartesian product, then you would take your two sets and write an x between them. So it looks like multiplication, but for a Cartesian product, you're always going to write an x. And just to make sure we understand how ordered pairs work, let's look at two small sets. To finish up class here. So I'm going to look at all ordered pairs, the Cartesian product of x and y. So it's a set where we have ordered pairs. The first element needs to come from x, the second element needs to come from y. Let's just take 1 and 1. And then I can also pair up 1 with 2 or 3. Okay, so now I've paired up 1 with everything over there. I have to stop using 1 as my first element. Let's go on to 2, and we can pair it up with 1. Go ahead.
Never mind. I was going to ask, why did you have 1, 2 labeled twice?
Good question. And let me finish writing this down, and I'll answer. The reason is that these are actually ordered pairs. So in a set, the order that you write things doesn't matter. When you're talking about ordered pairs, it does matter. Good question.
Yeah, but I'm asking, why didn't you put it down with 1, 1 instead of 1, 2?
Oh, okay. Here, that was just my hand was getting ahead of where it should have been. That should be a 1, 1. Thank you. Thanks for pointing that out. Okay, and these are all of the ordered pairs. I'm a minute over, but for those of you that are still here, let me point out that there are 6 ordered pairs here, and we have 2 elements in this set, 3 elements in that set. So we end up with 2 times 3 equals 6 ordered pairs. And this always works. If you need to count the number of ordered pairs that you're going to get from a Cartesian product, you multiply the number of elements in each set. So 2 times 3 equals 6 ordered pairs. And that's where this word, the product, comes in from this multiplication. Okay, any questions here at the end of class?
Can you possibly go over the example that was before this? That was the intersection of S is the intersection of all sets in S.
This one?
Yes.
Okay. So the intersection of a family is just the intersection of every set in your family. So if you're going to be an element in an intersection of a family, that means you have to be in each and every set in the family. Was your question about the definition or more about the answer to the question?
More about the answer.
Okay. So for this family, it's really big. So if you're going to be in the intersection, that means you have to be in each of an infinite number of sets. So you have to be in A1, A2, A3, A4, A5. You also have to be in a billion and three. So if we want to figure out the intersection, we have to decide if there's anything in all of these sets. And
Is it because you have to have them all in the same set? Like one has to be in each one of them and you're counting
Right.
up?
Exactly.
Okay.
Yeah. And when you move to the next set over, you're going to start at a bigger number. So you're going
Okay,
to,
so you won't have that one on there, so you can't include that in like your actual set.
right, because you're missing numbers. Yeah.
Okay, that makes sense.
Okay, good.
Thank you.
You're welcome. Okay, so if there aren't any other questions, you guys can all go. I'll stick around for a couple minutes just in case you think of something.
I have a question about the homework
Okay.
for number 53, where I draw a Venn diagram and shade in the given set.
Mhm. Okay, and it looks like there's also a question about 25. Okay, so I think this was what 25 was. So it's the union of x and the complement of y, and it's the same sets that we were talking about at the beginning of class. So if you want to answer this question, you have to think about what's in the complement of y. So what are the positive integers that are not in y? And should add a note here at the beginning that our universal set is the positive integers, z plus. So y has everything, all the even positive integers. So if you throw all of those out, what's going to be left are just the odd positive integers. So let's write that down here. The complement of y is equal to the odd positive integers, 1, 3, 5, 7, and so on. So I'll leave the last bit of writing down the answer to you, but you're going to take all of these elements, all these numbers, and combine them with these numbers. So you're going to add in a couple even numbers to all of your odd numbers. And then, Nick, you asked about problem 53.
Wait, so would it just be
Oh.
infinite How do we write down, like, 'cause it's going to constantly keep adding
Mhm.
positive odds?
An easy way to write it is using dots.
Okay.
So what the dots mean, they're called an ellipsis if you're in grammar class. But what they mean is that this pattern is going to continue. So 1, 3, 5, 7, and looking at these numbers, you can see what the pattern is. You know the next one should be 9. So if you write down the first few elements in this, and then you write a few more, and then a few dots so that I can see what the pattern is, that'll be perfectly fine. And then I believe 53 down here. So it's the complement of A, and then you're going to subtract B. So what you want to do to answer this question is to start by drawing a Venn diagram like I did on the notes. So make your box for the universal set. And then 2 circles for the 2 sets A and B. And then you have to figure out how to shade, what was it, A complement, and then subtract B. So Nick, where is A complement? So if I label them 1, 2, 3, and 4, which regions are A complement? This.
A 4 and 1.
4 and 1. Good. So A complement is everything out here, and then everything in B that doesn't overlap with A. Good. And if I subtracted off all the elements of B, what would be left? Which region?
The 1.
Right. So to answer your question, or to answer this question, you would just shade in that region. So everything out here.
Okay, that's what I thought. I just wanted to make sure.
Yeah. Okay, so it looks like we still have quite a few of you guys in here. Are there more questions?
So if I was to write 34, would I be using one of those rules? That's what I write the rule out, or would I just prove that B n equals 1, 2, and 3?
You said problem 34?
Yes.
Okay, so we're looking up here and we're trying to show that the 2 sets are equal to each other. So for 34, the way that I would approach this problem would be to look at this set B, which is in set builder notation, and try to figure out which numbers this actually includes. So reading this off, it's the set of n such that n is a positive integer and n squared is less than 10. So just figure out which numbers satisfy both of those conditions. So what positive integers square to less than 10?
1, 2, and 3.
Right. So just explain that in writing for your answer.
Oh, so like write it out in word form?
Professor Connor?
So you can use words and math, both. And was someone else saying something?
Yeah, that was Ethan. I actually have to run to another class. Sorry to interrupt, but
Oh, that's fine. Yeah, we're definitely running over here.
All right. But have a good day.
Thank you. You too. See you Wednesday.
Got it.
And I actually have to run as well. I have a 5:30 class that I
Hey,
need to get ready for.
Professor, what time would be okay for me to get in touch with you tomorrow if I have any more questions?
Tomorrow, between 10 and 12 are my office hours. So if you go ahead.
So if I wanted to do a Zoom conference call with you then?
Yeah. If you have questions, just send me an email between 10 and 12, and I'll send you a link.
All right, thank you.
You're welcome.